Hello there, and welcome to sleepy ancient Earth. Tonight, we drift down through 500 million years of ocean, to a moment when life first learned to build itself a body, the Cambrian, the Cambrian explosion. It was not quite a beginning, not quite a continuation, but something in between. A quiet world of soft-bodied drifters, suddenly filling out into shells, limbs, and eyes. The seas were warm, the land was bare. Some creatures grew the first hard shells the world had ever seen. Some dug down into the seafloor and turned firm microbial ground into soft, churned mud, opening whole new worlds to live in. Others raised the first eyes ever to catch the light of the sun, while a few, in warm and fertile shallows scattered across the equator, became the ancestors of nearly every animal alive on Earth tonight. If you enjoy these quiet journeys into the deep past, feel free to like and subscribe or share a thought in the comments below. It helps others find their way here too, one sleepy soul at a time. But for now, let's begin. The Cambrian period began about 541 million years ago. This is the line geologists draw to mark the start of animal life, as we would recognize it. Before that line, the fossil record holds mostly soft traces and faint impressions. After it, the rock fills with shells, limbs, and the first hard evidence of eyes. The boundary itself is not a single dramatic layer, but a slow shift, read across many sites and many kinds of stone. Where earlier seas held only the vaguest suggestion of bodies, Cambrian rock begins to hold their outlines with real clarity. To hold a piece of that boundary rock is to hold the last quiet moment before life became visible to itself. Nothing announced the change at the time. There was no line drawn in the mud, no signal in the water. Only, slowly, more and more creatures worth naming. The world did not know it was beginning something. It simply continued. And what continued became everything that followed. It followed directly after the long ice ages of the Ediacaran. For tens of millions of years before the Cambrian, the planet had locked itself in ice more than once, its oceans freezing nearly to the equator. Some geologists call this the Cryogenian, the frozen ages, and its glaciers may have reached from pole to pole. Whether the ice was truly global or left narrow strips of open water is still debated, and the rock does not settle the question fully. What is clear is that life endured it, thin and scattered, waiting in whatever water remained liquid. When the ice finally withdrew, the seas warmed and filled with nutrients scoured from the land. It was not unlike a long winter finally breaking, the world holding its breath before the thaw. Out of that thaw came the first true bloom of animal diversity. The cold had not ended life, it had only pressed pause on it, and the Cambrian was the sound of the pause lifting. The period lasted roughly 56 million years in total. Set against a human life, that number means nothing at all. And yet it is a short span by the standards of the rock beneath us. In that time, nearly every major body plan alive today made its first appearance somewhere in the world's shallow seas. Worms, arthropods, mollusks, and the earliest ancestors of backboned animals all found their basic shapes within this window. 56 million years is long enough for oceans to rearrange themselves, and short enough, in geological terms, to feel almost sudden. Compare it to the more than 3 billion years of mostly simple life that came before it. Against that backdrop, the Cambrian looks less like a chapter and more like a door swinging open. What walked, swam, and crawled through that door is still, in modified form, walking, swimming, and crawling today. The door did not close behind them. It simply widened, slowly, into everything that came after. Geologists named it after Cambria, the old Latin name for Wales. The rocks that first defined this period were exposed along the hills and coastlines of that region, layered plainly enough for a careful eye to read. Naming a period after a place is common practice in geology, tying a span of deep time to the exact rock where it was first recognized. Wales, in this sense, lent its ancient name to 500 million years of ocean history it never knew it contained. The choice had nothing to do with where Cambrian life was most abundant, since Wales sat far from the warm equatorial seas where most of it thrived. It was simply where the layers were legible. A quiet hillside, cut open by weather and time, became the reference point for an entire age of animal life. The name stuck, as such names often do, long after the reasons behind it faded from common memory. A small country gave its old name to an ocean that no longer exists. Adam Sedgwick first defined the period back in the 1830s. He was working through folded and faulted rock in Wales, trying to make sense of layers that seemed older than anything named before them. Geology at the time was still a young science, its timescale barely sketched, and each new period required painstaking fieldwork to separate one layer of rock from another. Sedgwick's Cambrian sat beneath rocks already claimed by a colleague working the same hills, and for years afterward, the boundary between the two periods was argued over in quiet, technical dispute. Fossils, more than rock alone, eventually settled where one period ended and the other began. What Sedgwick had found, without fully knowing it, was the base of the animal world as we understand it. He gave a name to something he could only partly see, working from exposed cliffs rather than complete answers. The full scale of what lay inside that name would not become clear for another century of careful digging. Earth's continents were scattered, with no single supercontinent yet formed. Unlike some periods in Earth's history, when nearly all land gathered into one great mass, Cambrian geography was fragmented and loose. Several smaller continents drifted independently across the globe, separated by wide stretches of ocean. Their positions were not yet fixed the way modern maps might suggest, and much of what is now Europe, Asia, and the Americas existed only as separate pieces, still finding their way toward each other. This scattering created many long coastlines and many separate shallow seas, each one a slightly different laboratory for early animal life. Where a single supercontinent might have limited the variety of coastal habitat, this fragmented world offered many. It is easy to picture continents as fixed and permanent, yet in the Cambrian they were still restless, still arranging themselves into the shapes the planet would carry forward. The map beneath the ocean was never finished. It was only, for a while, this particular arrangement of drifting stone. The ancient landmass Gondwana was slowly assembling near the equator. Pieces of what would later become Africa, South America, Australia, and Antarctica were drawing together during this period, though the process was far from complete. Sitting near the equator gave this early landmass a warm, wet climate along much of its coast, in contrast to the cold, ice-bound shape it would take hundreds of millions of years later at the far south of the globe. The seas fringing Gondwana were especially rich with early animal life, their warmth and shallowness ideal for creatures still working out how to build shells and limbs. It is strange to think of a continent now associated with polar cold, once resting comfortably in tropical waters. Positions on Earth are never permanent, only temporary arrangements held for a geological moment. Gondwana's equatorial youth left its mark in the fossil-rich rock still found across its now scattered pieces. A single landmass in its early years, cradling the first great bloom of animal shapes. Shallow, warm seas spread across continental shelves around the world. These were not deep ocean trenches, but sunlit margins, where light could reach the seafloor, and warmth lingered through much of the year. Continental shelves during the Cambrian were unusually broad, flooded further than in many later periods, creating vast stretches of gentle, livable water. Sunlight reaching the bottom allowed simple mats of microbial life to thrive there already, offering food and shelter to the small creatures beginning to crawl and burrow above them. Warmth encouraged faster growth and quicker reproduction, conditions that favored experimentation in body shape and behavior. A modern coral reef gives some sense of the light and warmth involved, though Cambrian shelves were softer, muddier, and far less structured. Nearly every major fossil site from this period comes from exactly this kind of setting, a shallow, sunlit shelf, rather than an open, empty ocean. The shallows, more than the depths, were where the early animal world chose to make itself known. Sea levels stood far higher than during most of Earth's history. Without large ice sheets to hold water on land, the oceans crept further onto the continents than they do today, flooding what would otherwise have been dry ground. This meant far more coastline overall, and far more of that coastline sitting in the warm, shallow conditions animals needed to thrive. Entire regions of modern continents, now well inland, once lay beneath a few meters of Cambrian sea. Higher sea levels also meant more stable, less turbulent water across these flooded shelves, since the waves had further to travel before reaching shallow ground. This calm, expansive flooding created enormous new habitat almost everywhere at once, rather than in a few isolated basins. A walk across a quiet inland field today might once have meant wading through knee-deep Cambrian water, thick with unfamiliar shapes. The sea did not just support Cambrian life. It made room for it, spreading itself generously across a young and welcoming world. Global climate ran warm, with little or no polar ice. Even at the highest latitudes, temperatures likely remained mild enough to prevent the thick ice caps familiar from later periods. This left the entire planet more evenly warm from equator to pole, without the sharp climate divisions that ice ages later carved into the world. A warmer, more uniform climate meant a wider band of habitable ocean, since fewer regions were locked away by cold. Warm water holds less oxygen than cold water. Yet Cambrian seas still supported an explosion of active, oxygen-hungry animal life, suggesting that oxygen levels were rising steadily through this period. The absence of ice also meant no vast frozen reservoirs locking water away from the oceans, keeping sea levels high and shelves flooded. It is a strange thought. A world with no ice at either end, spinning gently through its warm and settled seasons. The Cambrian earth carried its heat evenly, and in that mild, generous warmth, its animals found room to begin. Atmospheric oxygen kept rising, though still below modern concentrations. Through the early Cambrian, the air above the shallow seas grew steadily richer in the gas that animal life depends upon. Estimates suggest levels reached perhaps half of what the air holds today, a fraction that would leave a human lightheaded within minutes. Yet this was far more oxygen than the world had known through most of its earlier history, and for the small, hungry bodies of the Cambrian, it was enough. More oxygen meant more energy available for movement, for hunting, for building the muscle and nerve tissue that active life requires. Where earlier oceans could only support slow, simple organisms, these richer waters could sustain creatures that swam, chased, and fled. To breathe Cambrian air would have felt thin and strange to us, a world still catching its breath. The animals of this time did not need our air. They needed only enough to begin moving, and the ocean finally gave it to them. Ozone slowly accumulated, filtering more ultraviolet light from the sun. As oxygen built up in the atmosphere, some of it drifted high above the seas, and was transformed by sunlight into a thin protective layer. This early ozone shield was far weaker than the one that wraps the planet now. An ultraviolet light still reached the surface with considerable force. For animals living in shallow water, this mattered less than it might seem, since even a few meters of seawater blocked much of the harshest radiation. The shield's slow thickening mattered more for whatever life dared approach the surface or the exposed shoreline, where no plant or animal yet risked lingering. It is a quiet kind of protection, built not for any creature's benefit, but as a byproduct of the air itself changing. The sun still burned fiercely on that young world, but beneath the waves, in the blue Cambrian dark, life was already sheltered enough to begin its work. Calcium and carbonate grew more abundant in Cambrian seawater. Chemical changes deep in the earth, along with shifts in ocean circulation, sent these dissolved minerals flowing into the seas in greater quantities than before. Seawater carried more of the raw ingredients needed to build something solid, something that could hold its shape against the push of water and the bite of a hungry neighbor. Fossil evidence shows this mineral increase lining up closely with the sudden appearance of shells, spines, and plates across many unrelated lineages at once. No single animal invented hard parts. The ocean simply offered the materials, and life, scattered across dozens of separate branches, reached for them independently. This is not unlike a shared toolbox left open in a workshop, available to anyone who happened to need it. The Cambrian seas were quietly changing their own chemistry, and in that changed water, the first hard, lasting shapes of animal life began to form. This chemical shift may have made mineral skeletons easier to build. With calcium and carbonate readily available, the biological cost of forming a shell or a spine dropped considerably compared to earlier periods. Trilobites hardened their backs into overlapping plates. Brachiopods grew paired shells, and tiny cap-shaped creatures called hyoliths built cones they could retreat inside. None of these lineages copied one another. Each arrived at hardness through its own separate biochemistry, using the same abundant minerals the ocean now offered freely. A skeleton, once built, could support larger bodies, protect softer tissue, and leave behind something durable enough to fossilize for 500 million years. Soft-bodied ancestors before this time left almost no trace at all, dissolving quietly back into the sediment. The Cambrian was the moment biology first had something worth keeping. Not because life had grown ambitious, but because the sea had finally made permanence affordable. Land remained largely bare, covered only by microbial crusts and dust. Across the continents, no towering trees stood, no grass swayed, no green softened the endless stretch of exposed rock. A thin film of cyanobacteria and simple microbes clung to damp surfaces here and there, giving parts of the land a faint, dark sheen when wet. Wind moved freely across this open ground, kicking up fine sediment with nothing to hold it in place. What life existed on shore was invisible, without close inspection, a smear of biology rather than a landscape of it. The real activity of the Cambrian world remained entirely offshore, beneath the waves where warmth, food, and shelter were abundant. A continent in this era would have looked, from a distance, like a dead world circling a living sea. It was not dead. It was simply waiting, patient and unhurried, for life to find its way onto dry ground at last. No true soil yet existed to hold water or nourish roots. Soil as we know it forms slowly, built from decaying plant matter, fungal threads, and the tireless work of burrowing creatures, breaking rock down into something rich and dark. None of that existed yet, since none of its makers had appeared on land. Instead, bare mineral ground lay exposed to sun and rain alike, offering nothing for a root to grip and little to retain moisture after a storm. Rainfall that fell on Cambrian continents ran off almost immediately, carrying loose sediment straight toward rivers and eventually the sea. This meant a steady stream of nutrients pouring off the land and into shallow coastal waters, feeding the very ecosystems now filling with new animal life. Land's barrenness, in this strange way, became the ocean's fortune. What the continents could not yet use, the sea gratefully received, one quiet rainfall at a time. Rivers ran wide and straight without plant roots to anchor their banks. Without vegetation to hold soil in place, Cambrian rivers behaved very differently from the winding, tree-lined waterways familiar today. Water spread out across broad, shallow channels that shifted constantly, since nothing on the banks resisted the current's pull. Geologists studying rock layers from this period find braided patterns rather than the single meandering paths later rivers would carve once roots arrived to stabilize them. A river without anchoring plants is closer to a slow flood than a defined channel, spilling sideways whenever the ground allowed it. This constant reshaping sent enormous volumes of loose sediment downstream toward the coast, feeding the deltas and shallow shelves where Cambrian animals thrived. The rivers themselves left barely a mark on the landscape, erasing their own paths again and again. It was a world of water still learning how to hold a shape. Burrowing animals began reshaping the seafloor on a much larger scale. Earlier organisms had occasionally disturbed the top layer of sediment, but Cambrian creatures dug deeper, wider, and with far greater determination. Some traces preserved in ancient mudstone show vertical burrows reaching down as far as a human forearm, evidence of animals pushing steadily into ground that had never been disturbed before. This digging mixed oxygen into sediment that had once been stagnant, opening new pockets of habitable space beneath the seafloor's surface. Chemical conditions shifted as a result, and entirely new communities of tiny organisms began to live within the mud itself rather than only upon it. A seafloor once flat and undisturbed became something closer to a sponge, riddled with tunnels and shafts. None of the animals responsible knew they were transforming their world. They were only looking for food, and in searching, they rebuilt the ground beneath the entire ocean. This reworking of sediment is now called the Cambrian substrate revolution. Scientists use the term to describe the shift from a seafloor dominated by firm, undisturbed surfaces to one constantly turned over by burrowing and searching animals. Before this revolution, the ocean bottom behaved almost like packed sand, stable enough to walk across without sinking. Afterward, it became loose, soft, and unpredictable, closer to the shifting mud found in a modern estuary. This change did not happen everywhere at once, but spread gradually as burrowing behaviors became more common across many unrelated species. The consequences reached far beyond the animals doing the digging, altering how nutrients cycled through the sediment and how oxygen moved below the surface. A seafloor is not a fixed thing, even in the deep past. It responds to whoever lives upon it, and in the Cambrian, life finally arrived in numbers large enough to leave its mark. Firm microbial mats that once blanketed the seafloor began to vanish. For hundreds of millions of years before this, thin living carpets of cyanobacteria had coated much of the ocean floor, binding loose sediment into a stable, leathery surface. Cambrian burrowers tore through these mats as they dug, breaking apart a covering that had gone largely undisturbed since life first appeared in the sea. Without the mats holding it together, sediment grew looser and more mobile, changing the texture of the seafloor across wide stretches of ocean. Scientists studying rock from either side of this transition can see the difference clearly. Layered mat-bound stone giving way to the mixed, churned texture left by burrowing bodies. What had been a quiet, covered world became an open, disturbed one, shaped by movement rather than stillness. The mats did not disappear everywhere, but their age of dominance was ending. The Cambrian seafloor was learning, slowly, to be alive all the way through. Soft, churned mud replaced them as the new ocean floor surface. Where microbial mats had once held everything in place, the seabed now lay open and loose, shifting under the weight of anything that touched it. In some Cambrian rock formations, the mud layer runs several centimeters deep, soft enough that a falling body could sink rather than settle. This was not decay or ruin, only a different kind of ground, one built from motion instead of stillness. For burrowing animals, the change meant more room to hide, to feed, and to move unseen beneath the surface. A modern beach, raked smooth by every wave, gives some sense of how quickly such ground can change shape. To press a hand into that ancient mud, if such a thing were possible, would be to feel 500 million years of settling give way at once. The seafloor had traded permanence for possibility. This change opened new living space both above and below the seabed. Life in the earliest Cambrian seas had mostly spread sideways across a flat, shared surface, competing for the same thin layer of ground. Now animals could burrow down as deep as 10 centimeters, while others built tubes and shells reaching up into the water above. This was not simply more room, but a new kind of room, arranged in layers rather than laid out flat. Different creatures could feed, hide, and breed at different depths without ever crossing paths, easing the pressure of shared space. A modern coral reef shows the same principle at work, with life stacked from seafloor to surface rather than crowded onto a single plane. Imagine the Cambrian seabed after this shift, a building rising where once there had been only a single floor. Depth had become another kind of geography. Earth's day length kept stretching, though still short of 24 hours. Throughout the Cambrian, the planet was still recovering from a much faster spin inherited from its earliest history. A single day likely lasted close to 21 hours, packing many more days into each passing year than we experience now. The change came slowly, a matter of milliseconds added over centuries, driven by the pull of tides grinding against the shifting continents. For the earliest complex animals, this meant a world that turned faster beneath a sun that rose and set more often than it does now. A person standing on a Cambrian shoreline would watch the sun cross the sky noticeably quicker than it does today. The whole cycle compressed into fewer hours. Layers in ancient coral growth patterns still preserve this shorter rhythm, fine ridges marking each vanished day. The planet was still learning to slow down. The moon, still closer then, raised strong tides across shallow coasts. Early in Earth's history, the moon had formed much nearer to us, and though it had already drifted outward for billions of years, it remained closer during the Cambrian than it is now. Estimates place it perhaps 10,000 kilometers nearer, close enough to pull tides noticeably higher than today's. These were not violent surges, only a steady, forceful rhythm rising and falling across the shallow seas where most Cambrian life gathered. Twice each day, water swept sediment, nutrients, and small creatures back and forth across the coastal shelf, stirring the shallows into constant motion. A modern tide pool, refreshed each morning by the sea's return, offers only a faint echo of that ancient rhythm's strength. Standing on such a coastline, you would feel the sea's reach shift within a single afternoon, the shoreline redrawn twice between sunrise and dusk. The moon shaped the shore long before anything stood upon it to notice. Storms and tides likely shaped the shallow seas where most life gathered. Most Cambrian animals lived not in the open ocean, but along its edges, in shallow water, rarely more than a few dozen meters deep. Layers of storm-disturbed sand, sometimes over a meter thick, appear throughout Cambrian rock, evidence of seas regularly stirred by weather from above. These storms were not constant, only frequent enough to leave their mark, churning sediment and mixing oxygen-rich surface water down into the depths below. For animals living on the seabed, this meant a habitat that was never entirely calm, refreshed again and again by forces from far above the water. A modern storm surge along a shallow coastline offers some sense of the disturbance, sand shifting and settling long after the wind has passed. To live in these shallows was to exist inside a system built on interruption rather than calm, and to thrive because of it rather than despite it. The Cambrian shallows were restless, and restlessness fed them well. Volcanic activity along spreading ridges released carbon dioxide into the air. Beneath the Cambrian oceans, new seafloor was constantly forming along long volcanic ridges, where molten rock rose to fill the gaps between drifting plates. This process released carbon dioxide steadily, and some estimates suggest atmospheric levels several times higher than they are today. The release was gradual, spread across millions of years, rather than driven by any single eruption or event. That steady output helped keep the planet's climate warm through much of the Cambrian, holding the atmosphere in a state very different from our own. Today's atmosphere carries a fraction of that ancient carbon load, filtered and buried over hundreds of millions of years by rock, shell, and sediment. The air above the Cambrian seas would have felt heavier, warmer, and thick, with a chemistry unlike anything breathed since. Even stillness in this world was built from constant, unseen motion. That greenhouse warmth likely kept the oceans mostly free of ice. Warmed by high levels of carbon dioxide, the Cambrian world carried little of the ice familiar from more recent eras of Earth's history. Sea surface temperatures in many regions may have reached the high 20s in degrees Celsius, closer to a warm tropical sea than anything found near the poles today. Some ice may still have gathered at the planet's coldest extremes, though evidence for it remains thin and difficult to confirm. This warmth mattered enormously, keeping vast stretches of ocean open and hospitable to life across a much wider range of latitudes than ice ages allow. Where later periods of Earth's history locked whole oceans beneath frozen surfaces, the Cambrian seas stayed liquid, open, and full of room to spread. A swimmer moving through those waters would find them warm nearly everywhere, from the equator to the edges of the map. Warmth, more than any single creature, made room for the world to fill. Weathering rock washed nutrients into the sea, fertilizing coastal shallows. Across the Cambrian continents, rain and wind slowly broke down exposed stone, releasing minerals that rivers then carried down to the coast. Phosphorus and iron were among the most important of these, elements essential to building shells, tissues, and the chemistry of living cells. This process moved slowly, measured in centuries rather than seasons. Yet its effects accumulated steadily across the shallow seas, where life was gathering. Fed by this mineral wealth, plankton bloomed in greater numbers, forming the base of a food web that could now support far larger and more varied animals above it. A modern river delta, thick with nutrients carried from inland soil, still performs a quieter version of the same ancient work. It is as though the land itself had begun feeding the sea, one weathered grain of rock at a time. Nothing in the ocean grew without something first arriving from the shore. These fertile shallows became the stage for one of life's fastest transformations. Nutrient-rich water, warm seas, and newly opened living space combined here into conditions rarely repeated in Earth's long history. Within these shallow margins, nearly every major animal body plan alive today would find its earliest expression, from segmented limbs to hardened shells to the first true eyes. Fast, in this context, still meant many human lifetimes stacked end on end, though by geological standards, it was closer to an instant than an age. This concentration of change allowed evolution to test enormous numbers of body shapes and strategies within a relatively narrow span of time and space. Modern evolutionary change, by comparison, tends to unfold in far smaller, slower increments, without such a wide field of possibility opening all at once. Standing at the edge of one of these shallows, a person would witness the raw material of nearly all future animal life taking shape at once. The stage was fertile, and everything arrived to use it. Within roughly 20 million years, most modern animal groups' ancestors appeared. This span, brief by the standards of deep time, saw the arrival of body plans that would go on to define nearly every animal lineage alive today. Arthropods, mollusks, and the earliest chordates, distant ancestors of every fish, bird, and mammal to follow, all took shape within this narrow window. 20 million years sounds long, measured against a single life, yet set against 4 billion years of Earth's history, it passes in a breath. Scientists still debate exactly how sudden this appearance truly was, since earlier, softer ancestors may simply have left no trace for us to find. No comparable burst of new body plans has occurred since, even across the hundreds of millions of years that followed this one narrow chapter. Imagine an ocean where nearly every future shape of life first tests itself within the span of a single geological instant. The blueprint for almost everything alive today was drawn here, and then the drawing was set. This rapid burst of new body plans is called the Cambrian explosion. The name marks a period beginning about 541 million years ago, when the ocean floor filled with forms unlike anything that came before. Within a few million years, nearly every basic animal architecture we recognize today had already appeared in some early form. The word explosion is misleading in one sense, since nothing burst or shattered. It simply means that change arrived faster than in any other chapter of life's history. This burst gave evolution a vast library of shapes to draw from, many of which persist, refined but recognizable, in animals living now. Where earlier life had drifted through simple, soft forms for billions of years, this window compressed enormous innovation into a geological blink. Picture a shoreline where, layer by layer, the rock beneath your feet holds the record of that entire transformation. The name endures because nothing since has matched its pace. Charles Darwin worried this sudden appearance might undermine gradual evolution. Writing in 1859, he described the abrupt appearance of complex animals in Cambrian rocks as one of the most serious problems facing his theory of slow, incremental change. He proposed that earlier ancestors must have existed but had simply left no trace, perhaps because their bodies were too soft or the rocks too old and altered to preserve them. His concern was not that evolution was wrong, but that the fossil records seemed to skip the very steps his theory required. Later, discoveries have partly answered him, revealing simpler forms that predate the Cambrian by tens of millions of years. Still, the transition remains sharper in the rock than most of Darwin's other examples of gradual change. Imagine a naturalist a century and a half ago, troubled by a gap that would take generations of digging to begin closing. his doubt became one of paleontology's oldest and most patient questions. Simpler Ediacaran precursors have since eased some of that old concern. Before the Cambrian, during the Ediacaran period between about 635 and 541 million years ago, the seas held soft, quilted, often immobile creatures unlike anything alive today. Fossils such as Dickinsonia, an oval, ribbed organism with no visible mouth or limbs, show life experimenting with form long before hard shells or jointed legs existed. These creatures were not ancestors of every Cambrian animal, and many left no descendants at all. Their presence still matters, because they prove that complex, multicellular life existed well before the supposed explosion, quietly rehearsing. Where Darwin imagined an empty gap, the Ediacaran fills it with strange, tentative shapes. To look at a Dickinsonia fossil is to see evolution testing an idea it would later abandon. The Cambrian did not begin from nothing. It began from something already stirring. Molecular clock estimates suggest some animal lineages split earlier than fossils show. This method compares differences in the genetic code between living species and calculates how long ago their shared ancestor must have lived, using estimated rates of mutation. Some of these calculations push the divergence of major animal groups back beyond 700 million years, long before the Cambrian rocks record their appearance. The technique carries real uncertainty, since mutation rates are not perfectly constant and can vary between lineages and over time. Even so, it suggests that the ancestors of many Cambrian animals may have existed as small, soft-bodied creatures for tens of millions of years before leaving any visible trace. Fossils show us when a body became preservable, not when a lineage began. A living jellyfish and a living beetle may share an ancestor older than any rock we have ever dated. The clock and the stone keep different kinds of time. Fossils and molecular estimates still disagree on the timing of this split. In some cases, the gap between the two methods stretches across more than 100 million years, a period during which molecular models predict lineages existed, but no fossil confirms it. Part of the disagreement comes from the fragile nature of early animal bodies, most of which had no shells, bones, or hard parts capable of surviving burial and pressure. The rest may come from imperfections in the molecular clock itself, which assumes a steadiness that biology does not always provide. Neither record is simply right or wrong. Each preserves a different kind of evidence, one written in stone and one written in the chemistry of living cells. The record goes quiet here, leaving scientists to work with two maps that do not quite align. Somewhere in that silence, the true history of early animal life is still waiting to be read. For now, the disagreement itself is part of the story. Nearly every major animal phylum alive today appears within this narrow window. A phylum is a broad category of body plan, the kind of grouping that separates animals with backbones from animals with shells, or from animals with no hard parts at all. Of the roughly 30 phyla recognized today, the overwhelming majority have their earliest confirmed fossils in Cambrian rock, appearing within a span of perhaps 20 million years. Only a small handful of new body plans have appeared in the more than 500 million years since, and none has matched the scale of this early wave. This suggests that the basic architectural possibilities for animal life were mostly settled early, with later evolution refining existing plans rather than inventing new ones. Every backbone, shell, and segmented limb alive today descends from a design first tried in these ancient seas. The blueprints were drawn once and then followed with variation ever since. Nothing since has needed a new page. Arthropods, animals with jointed legs and hard shells, diversified explosively. By the middle of the Cambrian, Arthropods already accounted for a large share of all animal fossils found in the richest deposits, more than any other group. Their jointed exoskeletons, made of a tough material called chitin, allowed movement, protection, and growth through periodic molting, shedding an old shell to grow a new, larger one. This flexible design let arthropods adapt to nearly every available niche, from swimming and crawling to burrowing through soft sediment on the seafloor. Modern arthropods, including insects, spiders, and crustaceans, now make up the majority of all animal species on Earth, a legacy stretching directly back to this early success. Where earlier animals were soft and slow, arthropods moved with purpose, protected by armor that could bend without breaking. A single design, repeated and adjusted, came to fill nearly every corner of the living world. Few inventions in life's history have traveled so far. Trilobites, an early and abundant arthropod group, spread through nearly every sea. These flattened, segmented creatures ranged from smaller than a fingernail to nearly the length of a forearm, and their fossils have been found on every continent on Earth today. Trilobites persisted for over 270 million years, longer than the dinosaurs would later survive, making them one of the most enduring animal designs ever recorded. Their hardened exoskeletons, made of calcite, fossilized easily, leaving behind one of the richest and most detailed fossil records of any ancient group. Because of this abundance, trilobites now serve as a kind of clock for geologists, helping to date the rock layers in which they are found. Where most Cambrian creatures vanished, leaving only fragments, trilobites left whole and detailed forms behind. Walking across certain hillsides today, a person might unknowingly cross the compressed remains of thousands of these ancient sea dwellers. Their armor outlasted the seas that once held them. Their compound eyes, built from many lenses, were among the first complex eyes. Some trilobite species carried thousands of individual lenses within a single eye, each one a tiny calcite crystal arranged to capture light from a slightly different angle. This design produced a coarse but functional mosaic image, useful for detecting movement and shape rather than fine detail, much like the eyes of a modern dragonfly. Because calcite crystals fossilize well, these eyes remain visible in stone today, giving scientists a rare direct look at how ancient animals may have seen their world. Before this, most animals likely sensed only light and shadow, without any true image forming from what they detected. The arrival of a working eye changed the terms of survival, turning the ocean into a place where shape and distance suddenly mattered. Holding a trilobite fossil up to the light lets a person glimpse a version of sight built 500 million years ago. Sight, once rare, became one of life's most valuable inventions. Vision itself may have driven much of this evolutionary acceleration. One hypothesis, sometimes called the light switch idea, suggests that once a handful of animals developed working eyes, every other creature in the water faced sudden new pressure to hide, flee, or fight back. Predators with sight could locate prey far more efficiently than those relying on touch or chemical cues alone, and prey with sight could detect danger before it arrived. This created a feedback loop, where each improvement in vision or defense pushed rivals to adapt in turn, accelerating change across many unrelated lineages at once. The idea remains debated, since eyes were only one of several innovations, including hard shells and active swimming, appearing around the same time. Even so, many researchers agree that the sudden usefulness of sight likely reshaped behavior across the entire Cambrian seafloor. A world once navigated by touch and drift became, almost overnight in geological terms, a world watched. Seeing, once it began, could not be undone. Once one animal could see, hiding suddenly became a necessary skill. Across the Cambrian seafloor, the arrival of functioning eyes turned open water into exposed ground, and every soft-bodied creature, without armor or speed, now carried a target on its back. Trace fossils from this period show burrows suddenly reaching deeper into the mud, some descending twice as far as those found in rock, only a few million years older. This was not choice in any deliberate sense, only the slow filtering of those who happened to burrow deeper, surviving longer than those who did not. Concealment became as valuable as strength, and the sea floor itself began to fill with hidden lives rather than exposed ones. Where earlier animals drifted openly across the mud, their descendants learned to vanish beneath it. A person walking along a beach today, watching a crab vanish sideways into sand, is watching a habit that began the moment sight entered the sea. Hiding, once unnecessary, became the difference between eating and being eaten. This idea is sometimes called the light switch hypothesis, though still debated. First proposed to explain why so many hard parts and complex behaviors appeared within such a narrow span of geological time. It treats vision as the single spark that ignited a broader chain of adaptation. Critics point out that oxygen levels were also rising sharply during this same window, and that genetic changes, allowing more complex body plans, may have been building for tens of millions of years beforehand. The truth likely involves several causes acting together rather than one dominant trigger. Still, the timing remains striking, since eyes, shells, and active predation all appear within a few million years of one another in the fossil record. No single fossil can settle the argument, only patterns across thousands of them. Someone weighing these ideas today might picture the Cambrian less as a single switch flipping and more as several dials turning together. Sometimes a good explanation must remain shared among several quiet, competing ideas. Hard skeletons appear almost simultaneously across many unrelated animal groups. Trilobites, brachiopods, mollusks, and early arthropods all began secreting mineral coverings within a span of perhaps 20 million years. A narrow window by the standards of deep time. These skeletons were not inherited from a shared ancestor, since the lineages themselves diverged long before hard parts appeared, each independently discovering how to draw minerals from seawater and build them into shells. This pattern is called convergent evolution, when unrelated organisms arrive at similar solutions to the same problem without sharing the invention itself. Soft bodies that once left only faint impressions in mud began leaving durable shells that could last for hundreds of millions of years. A tide pool full of shells today holds, hidden within it, the echo of that first scattered rush toward armor. Protection, once rare, quickly became common sense. Shells, spines, and plates offered protection against newly emerging predators. Wiwaxia, a small oval creature that grazed along the seafloor, carried rows of hardened spines rising from its back, while Hallucigenia wore overlapping mineral plates across its length like an armored ribbon. These defenses were rarely absolute, since even a fully plated animal remained vulnerable at its joints, its underside, or the moment it needed to move quickly. Armor also carried a cost, since a heavier body meant slower movement and greater energy spent simply carrying its own protection. Every design was therefore a compromise between safety and mobility, worked out differently across dozens of separate lineages. Much like a modern armadillo trades speed for a shielded back, these early animals traded openness for survival, each choosing its own balance. A fossil imprint of Wiwaxia's spines is one of the clearest windows we have into just how seriously that trade was taken. Defense in the Cambrian Sea was never free. Predation becomes common and visible throughout the Cambrian fossil record. Burgess Shale specimens alone preserve dozens of instances where one animal was clearly caught in the act of consuming another, something almost never seen in the softer, gentler world that came before. Distinguishing true predation from simple scavenging remains difficult, since a fossil can rarely reveal whether a bite came before or after death. Even so, the sheer number of damaged shells, severed limbs, and half-digested remains suggests that active hunting had become a normal part of daily survival. Earlier Ediacaran communities show almost no comparable evidence, their inhabitants apparently grazing and filtering in relative peace. Food webs grew tangled almost overnight, each species now connected to several others through the simple fact of eating or being eaten. To look closely at a Burgess Shale slab is to see, layered in stone, the moment peaceful grazing gave way to constant vigilance. The sea had learned to feed on itself. Bite marks and healed injuries appear far more often than before. Trilobite fossils from several Cambrian sites show shells with asymmetrical scars along one side, places where the exoskeleton was broken and then regrew slightly out of alignment during the animal's next molt. At some localities, healed injuries appear in roughly 1 out of every 20 specimens collected, a striking rate for creatures with no bones to set or wounds to bandage. These marks tell a hopeful story rather than a grim one, since a scar means the animal survived whatever attacked it and lived long enough to shed its skin again. Such evidence lets researchers estimate how common failed attacks were compared to successful ones, offering a rough measure of how dangerous daily life had become. A house cat carrying a healed scratch along its ear shows the same basic pattern, survival written quietly into old damage. Every scarred trilobite is a small record of an escape rather than an ending. Injury, it turns out, could also be a kind of evidence for resilience. An arms race between hunter and hunted may have sped new designs along. As predators grew better at breaking through shells, prey animals responded with thicker plating, sharper spines, or faster means of escape. And as prey improved their defenses, predators in turn developed stronger mouths or quicker strikes. This back and forth did not happen through any single dramatic contest, but through countless small advantages accumulating across many generations. Trilobite shells from later Cambrian layers tend to be thicker and more elaborately ridged than those from earlier ones, a pattern that lines up with the rise of shell-crushing predators during the same period. Such feedback loops can push evolutionary change far faster than gradual drift alone, since neither side can afford to remain still while the other adapts. A cheetah's speed and a gazelle's own quickness reflect the same ancient logic, worked out over millions of years instead of a handful. In the Cambrian seas, this pressure compressed what might have taken far longer into a comparatively brief and busy chapter. Change, once contested, rarely moves slowly. Anomalocaris, a meter-long swimming predator, ranked among the era's largest animals. Most other Cambrian creatures were no longer than a human finger, so an animal stretching the length of a canoe paddle would have seemed almost impossibly large moving through the water above them. Its body was long and segmented, lined with flexible flaps that rippled in sequence to push it forward with surprising speed for its time. Nothing else in the Cambrian seas approached its size, and for several million years it likely faced no serious rival near the top of the food chain. Being the largest animal alive carried its own kind of vulnerability, since a body that size needed a steady and reliable source of food to sustain it. Imagine standing at the edge of that ancient sea and watching a shape the length of an oar drift past overhead, dwarfing everything beneath it. Its size alone would have reordered the sea's entire sense of scale. Being large in that early ocean meant becoming impossible to ignore. Its circular mouth held serrated plates for crushing armored prey. Arranged in a ring of roughly 30 overlapping segments, the mouth could contract inward like a slowly closing aperture, applying steady pressure rather than a single sharp bite. Unlike the hinged jaws familiar from later animals, this structure had no upper or lower half, only a circle of plates working together toward the center. Such a design suited a diet of trilobites and other shelled creatures, since a squeezing motion could crack open armor that a single point of pressure might simply glance off. Fossil evidence remains mixed on how often this method actually succeeded, since few trilobite shells show the kind of clean circular damage the mouth would have left behind. The mechanism resembles a nutcracker turned inward on itself, patient and mechanical rather than quick. A person watching that ring of plates slowly tighten around prey would see mechanics before violence, patience before speed. Even predation, in its first age, could still look strange. Two long, spiked limbs near its head likely helped grasp struggling prey. Each limb carried a row of inward curving spines along its length, forming a shape well suited to pinning down a soft-bodied animal or holding a trilobite steady while the mouth did its work. Some fossils show these limbs folded close to the body, suggesting they could be drawn in when not needed, much like the grasping arms of a modern mantis shrimp at rest. Their exact function remains only partly understood, since spines suited for holding prey could also have served in sensing vibrations through the water. Whatever their full purpose, their presence points to a predator built with more than one tool for securing a meal. A limb capable of grasping added precision to a body already built for reach and speed. Watching such an animal hunt would have meant watching several systems work together at once: mouth, limbs, and body moving in coordination. Anomalocaris was not simply large, it was, in every sense, well equipped. Opabinia, a strange five-eyed creature, used a long, flexible nozzle instead of jaws. It drifted through the shallow seas of the Cambrian, a world still experimenting with the basic architecture of bodies. Its 5 eyes sat atop its head on short stalks, while a long proboscis, tipped with small spines, extended forward to gather food from the seafloor. This nozzle was not a mouth in any conventional sense, but an extension that carried food back to an opening beneath the head. Such a design allowed Opabinia to probe crevices and soft sediment without needing to bring its whole body close to danger. Where later animals refined mouths into fixed points of intake, Opabinia kept its options mobile, reaching rather than approaching. A creature feeding this way seemed to sample its surroundings, the way a hand might feel along a shelf in the dark. It was a body built from spare parts of ideas that had not yet settled into place. Its unusual design puzzled scientists for decades after its discovery. When Opabinia was first assembled from crushed Burgess Shale fossils, its features seemed to belong to no known group of animals at all. Early reconstructions in the 1970s drew laughter at a scientific conference, since nothing about the body seemed to fit together in any familiar way. This confusion was not a failure of observation, but a sign of how differently early animals could be built, before evolution had settled into its later, more consistent patterns. Understanding Opabinia eventually helped researchers recognize a broader group of soft-bodied Cambrian animals related to modern arthropods, insects, spiders, and crabs among them. Modern animals often sort quickly into familiar categories, but Opabinia resisted every attempt at easy classification. Imagine holding a fossil and finding that nothing in the animal kingdom quite explains what lies in your hands. Some puzzles, once solved, only reveal how strange the beginning of life truly was. Hallucigenia, a spiny worm-like animal, was originally reconstructed upside down. It lived among the soft sediments of the Cambrian seafloor, a small creature no longer than a finger. Early illustrations placed its rigid spines beneath the body, walking on them like stilts, while soft tentacles were drawn along the back. This reading of the fossil later proved reversed. Once clearer specimens showed the spines belonged along the top and the legs beneath. The correction mattered because it changed how researchers understood the animal's balance, movement, and place among other Cambrian creatures. A body once imagined tottering on rigid points was, in truth, walking softly while defended from above. To picture Hallucigenia now is to picture a creature armored like a hedgehog set upright on its feet, spines raised toward whatever might threaten it from overhead. Even the shape of an animal can wait millions of years to be read correctly. Later studies showed its spines lined its back, not its underside. This correction came from fossils preserving a full row of stubby legs along the belly, invisible in earlier, poorer specimens. Each spine was hollow and slightly curved, arranged in pairs down the length of the body, 7 pairs in total, forming a jagged ridge along its length. The legs beneath ended in small claws, delicate enough to suggest a slow, careful gait across soft mud rather than any rapid pursuit. This new orientation solved a long-standing puzzle about how such a creature could have moved at all, with its spines pointed downward. Once turned right side up, Hallucigenia made sense as a grazer, picking its way across the seafloor, while its spines discouraged anything larger from settling too close. A listener imagining it now might picture a slow, spiny caterpillar easing along an ancient floor, patient and unbothered. The animal had not changed. Only the way it was seen had. Wiwaxia, a scaled, slug-like animal, wore overlapping plates for defense. It crept across the Cambrian seafloor on a broad, muscular foot, much like a modern slug easing over a garden path. Its back carried rows of flattened scales, layered like roof tiles, with 2 long rows of upright spines rising from the sides for added protection. These plates were not made of bone or shell in the way we know them, but of a tougher organic material, whose exact chemistry remains only partly resolved. Such armor likely deterred smaller predators, while allowing Wiwaxia to continue its slow grazing across mats of bacteria and algae on the seafloor. Unlike animals that fled from danger, Wiwaxia simply endured it, relying on its covering rather than its speed. A hand passing gently over its back, were such a thing possible, would find something between a scale and a leaf, neither fully hard nor fully soft. Defense in this world did not always mean movement. Sometimes it meant simply being difficult to open. Pikaia, a slender swimming creature, may be an early relative of vertebrates. It swam above the seafloor in gentle undulations, a shape closer to a flattened leaf than to any fish familiar today. Fossils found in the Burgess Shale show a body about 5 centimeters long, roughly the length of a human thumb, with faint traces of muscle segments running down its sides. Whether Pikaia truly belongs on the direct line to vertebrates remains debated, since several Cambrian animals show similar features without being closely related. Its importance lies less in certainty and more in what it represents. An early attempt at the body plan that would eventually lead to fish, and then to every animal with a backbone. Where most Cambrian creatures were armored or many-legged, Pikaia was simple, soft, and built for open water rather than the crowded seafloor. Imagining Pikaia swimming means imagining one of the quietest beginnings of our own family history, unremarkable in its own time. Nothing about it announced what it might become. Its simple notochord, a flexible rod along its back, hints at our own ancestry. This rod ran the length of Pikaia's body, providing stiffness against which muscles could pull, allowing the smooth side-to-side motion of swimming. In humans, this same structure appears briefly in early embryonic development before being replaced by the bones of the spine. The notochord did not yet carry nerves or protect them the way a spinal column would later come to do, and it offered support alone. Its presence, however humble, marked a structural choice that would echo forward through hundreds of millions of years of animal life. An insect, instead, relies on an external shell for support, while Pikaia and its descendants built support from within, a rod running through the center of the body. A finger traced down your own back would follow, faintly, the descendant of that same idea. A small rod in a small animal, and yet everything with a spine follows from it. Haikuithis, found in China, may be among the earliest fish-like animals known. It appears in rocks near the town of Haiku in Yunnan province, deposited during the early Cambrian some 518 million years ago. The animal measured barely 2.5 centimeters, smaller than a paperclip. Yet its fossils preserve traces of a head, gill structures, and a row of fin-like folds along its back. Calling it a fish requires some caution, since it lacked the bones, scales, and jaws that define fish in the modern sense. Even so, its features place it closer to true vertebrates than almost anything else known from its time, a possible early branch on the road toward backboned life. Compared to the armored, many-legged animals crowding the Cambrian seafloor, Haikuithis was small, soft, and easily overlooked. A collector sifting through shale in Yunnan might have passed over it entirely, mistaking it for a smear of carbon rather than an ancestor of nearly every animal with a spine alive today. It survived in the rock by accident, and in doing so changed how the story of vertebrates begins. It had a distinct head region and rows of simple muscle blocks. Fossils show a slight thickening at one end of Haikuithis' body, containing structures interpreted as simple sensory organs and possibly a rudimentary brain. Behind this head, muscle blocks called myomeres, shaped like stacked chevrons, ran down each side of the body in a pattern still visible in fish today. Scientists remain uncertain how complex this early brain truly was, since soft tissue rarely survives well enough to reveal fine detail. Regardless of its limits, this arrangement of head and segmented muscle gave Haikuithis a controlled, directional way of swimming that many of its contemporaries lacked. A jellyfish drifts wherever the current takes it, while Haikuithis could choose a direction and hold to it, however feebly. Looking closely at those muscle blocks reveals the outline of a pattern still written into the body of every fish that swims today. The blueprint was rough, but the blueprint was there. Early chordates lacked jaws, bones, or fins in any modern sense. Haikuithis, Pikaia, and their few known relatives represent a stage before any of these features had appeared. A body plan still built from soft tissue and simple support structures. Jaws would not evolve for tens of millions of years, arising later from the reshaping of gill supports in early fish. Bone was absent entirely, replaced by cartilage-like tissue, or, in Pikaia's case, the notochord alone, offering support without the weight or rigidity of a skeleton. This absence was not a deficiency, but simply the current stage of a body plan still being tested, one still open to whichever changes proved useful. A shark today still carries this ancient inheritance, its skeleton made of cartilage rather than bone, a quiet echo of these first chordates. To watch one of these small Cambrian swimmers move would be to watch a body still deciding what kind of support it needed. Everything that came after, jaws, bone, fin, and scale, was still millions of years away, waiting in the soft tissue of animals like these. Sponges built some of the first true reef structures on Earth. Long before coral existed, the seafloor still rose into ridges and mounds shaped by living things. These early sponges secreted rigid frameworks of calcium carbonate, cementing themselves together into structures that could stand as tall as a person. They were not solitary animals, but colonies. Thousands of individuals fused into a single standing form. Their presence changed the shape of the shallow seas, creating the first hard architecture that other creatures could gather around, hide within, or climb over. Where before there had been only sediment and drifting bodies, now there was structure, fixed and lasting. To swim past one of these early reefs would be to see the seafloor rise into shape for the first time in the story of life. The reef itself was new, the reef builders barely more than glued together specks. Archaeochaethids, cup-shaped reef builders, formed extensive limestone mounds in shallow seas. These creatures resembled sponges, but built their bodies from double-walled cones, porous like a strainer, stacked and clustered until they formed banks of stone. Some mounds stretched for hundreds of meters along the seafloor, built cup by cup over the span of a few million years. No single archaeochaethid lived long or grew large, but together their skeletons accumulated faster than the sea could wear them away. Their reefs created the first large-scale calcium carbonate deposits on Earth, a foundation later generations of reef builders would inherit and rebuild upon, after archaeochaethids themselves vanished. A coral reef today still follows this same principle, of small lives adding up to something none of them could have built alone. Standing on such a mound, could a person have stood there, they would have felt solid ground made entirely of the dead. It is as though the sea had begun, quietly, to keep its own records in stone. These reefs offered shelter and hunting ground for countless smaller creatures. Within the crevices and hollows of the archaeochaethid mounds, a second world took shape, tucked out of the open water above. Worms threaded through the gaps between cups, while small arthropods clung to the reef's uneven surface, feeding on whatever drifted close. The reef itself did nothing to protect these tenants deliberately, but its shape alone was enough, offering cover from currents and from anything larger swimming past. This was among the first times a physical structure, rather than open water or bare sediment, shaped where life could gather and how it behaved. A forest today shelters its undergrowth in much the same way, offering shape rather than intention. To look closely at a fossilized reef is to find, pressed into its gaps, the outlines of lives that depended entirely on a structure they had no part in building. The builders asked for nothing back. Brachiopods, shelled filter feeders resembling clams, became common across shallow waters. Though they look like bivalve mollusks at a glance, brachiopods evolved their two shells along a different axis of the body entirely, unrelated in ancestry to true clams. Their shells opened and closed around a coiled feeding organ called a lophophore, which drew in water and filtered out particles of food suspended within it. Fossils of these shells appear by the thousands in Cambrian rock, suggesting they lived crowded together across vast stretches of the seafloor. Their success lay not in speed or defense, but in patience, sitting fixed in place and letting the sea deliver its food to them. Where an animal like Anomalocaris pursued its meals, the brachiopod simply waited for the water to bring its own. To find a bed of brachiopod shells in the rock is to find a record of stillness, thousands of lives spent in one place. Few animals since have made patience so complete a strategy. Mollusks, including early snails and their kin, diversified into many new shapes. Among the shelled creatures spreading through Cambrian seas, this group tried out forms that would echo for the rest of life's history. Some built simple, coiled shells barely larger than a grain of rice, while others grew shells shaped like caps, cones, or gently curved tubes. Their soft bodies rarely fossilize, so most of what survives is the shell alone, a hardened outline of a life whose details remain hidden. Even so, these shells reveal a body plan flexible enough to be reshaped again and again, a flexibility that would later produce squid, octopuses, and garden snails alike. A single family tree, stretched across 500 million years, holds creatures as different as an oyster and an octopus. To hold a Cambrian snail shell is to hold the first rough draft of a shape still being written today. The shell was simple. What it would become was not. Echinoderms, the group including starfish, experimented with unusual body symmetries. Modern starfish and sea urchins share a 5-part symmetry, radiating outward from a central point like a wheel with spokes. Cambrian echinoderms had not yet settled into this pattern, and fossils from this period show a startling range of alternative arrangements instead. Some had bodies with no symmetry at all, oddly lopsided and fixed to the seafloor by a single stalk. This variety suggests that 5-part symmetry, so familiar in tide pools today, was only one solution among many that early echinoderms tried before natural selection settled on it. Where a human body divides neatly along a single line, these creatures were still testing whether any line should exist at all. To look at a Cambrian echinoderm fossil is to see a body plan still arguing with itself over its own shape. The 5-pointed star came later, once the argument had settled. Some early echinoderms show threefold or asymmetrical forms, unlike their living relatives. Among the strangest of these was a creature called Hallucigenia, its plated body coiled like a spinning top, rather than spread into a star. Its plates spiraled around the body in a pattern with no clear left or right, no obvious front or back, a shape that fits no living echinoderm alive today. Scientists believe it lived partly buried in sediment, feeding through a mouth positioned somewhere along its spiraled side. Such forms did not persist, and by the close of the Cambrian, the 5-part body plan had become the standard the group would carry forward. A spinning top, once set turning, eventually settles into stillness, and something like that happened here, across millions of years rather than seconds. To picture Hallucigenia is to picture a shape evolution considered once and then quietly set aside. The fossil record kept it, even though the ocean did not. Priapulid worms, armed with spiny retractable mouths, burrowed through Cambrian sediment. These worms moved through the soft seafloor in search of prey, their bodies soft and unsegmented, but capable of surprising force. Their mouths, when extended, turned inside out, presenting rows of small spines like an inverted glove lined with hooks, before withdrawing back into the body. This structure allowed them to seize smaller worms or drifting particles and pull them directly into a waiting gut. Priapulids remain alive today in cold, muddy seafloors, largely unchanged in form across 500 million years, making them one of the Cambrian's most faithful living echoes. A creature so old moving through mud today carries, essentially unaltered, the same hunting method its ancestors used before there were fish, before there were forests. before there was almost anything else. To find a priapulid burrowing through modern sediment is to find a Cambrian hunter still quietly at work. The method needed no improvement. It has simply continued. Most Cambrian animals were small, rarely longer than a human finger. Beneath the more famous giants of the period, the sea was dominated by creatures easily overlooked, some barely visible without close attention. Trilobites often measured only a few centimeters. Worms rarely exceeded the length of a hand, and countless soft-bodied animals were smaller still. This modest scale was not a limitation, but a fit, suited to a world of shallow water, limited oxygen, and predators only beginning to grow teeth and claws. Smallness offered its own advantages, letting a creature hide in narrow gaps, drift unnoticed, or simply need less food to survive each day. A world scaled to the length of a finger can still hold immense complexity, every joint and eye and gut fitted into a space smaller than a coin. To imagine the Cambrian seafloor is to imagine a crowd of small lives, each one modest, together forming something vast. Size was never the point. Survival was. A few, like Anomalocaris, reached sizes closer to a grown adult's arm span. Against the small crowd of Cambrian life, such creatures stood out simply by being seen from a distance, visible where most others required a careful eye. Anomalocaris could grow beyond 1/2 meter in length, its segmented body trailing fins along each side and 2 grasping limbs curling from its head. Fossils suggest it hunted trilobites and other hard-shelled prey, though whether it could actually crack their shells remains uncertain, since its mouthparts appear delicate for such work. Its size alone marked a shift, showing that a body plan built from soft segments and paired limbs could scale up into something the Cambrian seas had not held before. Where most animals of the time could be cupped in a hand, Anomalocaris required both arms extended to measure. To see one drifting through open water would be to see the Cambrian ceiling being tested for the first time. The sea had grown large enough to hold something that size at last. Most Cambrian seas held no true vertebrate predators of significant size. The animals ruling this world were built from shells and jointed limbs, not spines and backbones. Vertebrates existed only as small, eel-like creatures, rarely longer than a few centimeters, filter feeding near the seafloor rather than hunting. This absence is easy to miss, since later oceans came to be defined by fish, sharks, and eventually the vertebrate body plan that includes our own. Without large vertebrate hunters, arthropods and their relatives filled every predatory role available, from ambush to pursuit. The seas we know today, patrolled by creatures with backbones from top to bottom, would have looked almost unrecognizable to a Cambrian eye. To swim through this ocean would be to find no fish waiting in the shadows, only shells and legs and eyes on stalks. The vertebrate age was still tens of millions of years away. Plankton, tiny drifting organisms, diversified rapidly, feeding a growing food web. Beneath the visible drama of trilobites and swimming predators, an invisible economy was expanding in the open water above. Within a few million years, over a dozen new lineages of microscopic plankton appeared, some encased in mineral shells no wider than a grain of sand. These were not simple passengers of the current, but active feeders, straining nutrients from the water and multiplying by the billion. Their abundance meant more food drifting downward to the seafloor, supporting animals that could never have survived on scarcity alone. Where earlier oceans held thin, patchy plankton, the Cambrian Sea grew thick with drifting life, cloud after cloud of it suspended in the light. A single cup of that seawater might have held thousands of tiny lives, each too small to notice. Together, forming the base of everything larger. The whole edifice above the seafloor rested on something almost too small to see. Acritarchs, ancient organic walled microfossils, shifted shape and diversity through this interval. These are the fossilized remains of single-celled organisms, likely algae, preserved as tough organic walls that survive long after the cell itself decays. Through the early Cambrian, acritarch shapes multiplied from a handful of simple spheres into hundreds of spiny, ornamented forms, each distinct enough to identify. Scientists still debate what many of these organisms actually were, since the fossils preserve only an outer wall and nothing of the life within. Their sudden variety mirrors the burst of larger animal life happening at the same time, suggesting the whole ocean, from the smallest cell upward, was experimenting with new forms. Geologists now use these tiny fossils to date rock layers with more precision than almost any other method available from this period. A single grain of ancient mud might hold hundreds of these shapes, each one a fingerprint of a particular moment in time. The smallest fossils often tell the most exact stories. Ecosystems develop distinct vertical layers, from seafloor dwellers to open water swimmers. Life no longer occupied a single flat plane along the ocean floor, but stacked itself upward through the water column in overlapping zones. Close to the mud, burrowing worms and stationary filter feeders anchored themselves to one spot, drawing food from water passing just above them. A little higher, crawling arthropods and slow-moving mollusks picked their way across the surface, while further up still, active swimmers patrolled open water, untouched by anything below. Each layer used the same volume of sea differently, avoiding competition simply by living at a different height. A modern coral reef shows the same idea today, with fish sorted by depth as clearly as books on a shelf. Descending through a slice of Cambrian ocean meant passing through several separate worlds, each only a few meters from the last. Height, as much as location, had become a kind of address. This layering, called tiering, let more species share the same patch of seafloor. Paleontologists use the word to describe how ecosystems divide vertical space, stacking different lifestyles instead of spreading them thin across a single surface. Cambrian tiering reached only a few centimeters above and below the mud, modest compared to the meters-high burrows and towering kelp forests of later oceans. Even that small amount of vertical space made a measurable difference, allowing many more species to coexist without direct competition for the same food or shelter. Before tiering developed, ecosystems were flatter, and diversity was limited by how much of that single surface could be divided among competing forms. It is a bit like a small town growing into a city, adding new floors instead of only new streets. Standing on a Cambrian seafloor, a person might have felt life pressing close from below, beside, and just above, layered like sediment itself. Complexity, it turns out, can grow upward as easily as outward. Genetic switches, called Hox genes, controlling body layout, predate this burst. These genes act like an instruction set, telling a developing embryo where to place a head, a limb, or a segment along its length. Versions of Hox genes appear in animals long before the Cambrian, embedded in the DNA of soft-bodied ancestors that left barely any fossil trace at all. This means the biological toolkit for building complex bodies existed well before those bodies actually appeared in the rock record, waiting rather than absent. The genes themselves did not need to be invented during the explosion, only rearranged, duplicated, or expressed in new combinations. It is a little like a set of tools sitting unused in a workshop, long before anyone builds the furniture they were meant for. Fossils cannot show us genes directly, but comparing living animals lets scientists trace this toolkit back far earlier than any Cambrian shell. The instructions came first. The building came later. Small changes to these ancient switches may have unlocked new body shapes quickly. A single mutation in a Hox gene can shift where a limb grows, how many segments a body has, or whether an eye develops at all. Because these genes control entire developmental cascades, altering one switch can ripple outward into a completely different body plan without requiring thousands of separate changes. This offers one explanation for how so many new forms appeared in such a narrow span of geological time, since evolution did not need to build complexity gene by gene. A shift that once took enormous spans of time to accumulate could, through this method, happen across only a handful of generations. Where older models imagined evolution creeping forward in tiny steps, this mechanism allows for sudden, visible leaps in form. A single altered switch might turn a simple worm-like ancestor into something bearing legs, eyes, or a hardened shell almost overnight, in evolutionary terms. Small causes can hold surprisingly large consequences. Whether new genes or new ecology drove the explosion remains debated. Some researchers argue the genetic toolkit was the true trigger, unlocked switches finally permitting bodies that could not have existed before. Others argue that ecological pressure came first, with rising oxygen, new predators, and crowded seafloors forcing existing genetic potential into new expression. Both explanations rest on solid evidence, and neither fully accounts for the timing on its own, since the genetic tools existed long before the burst. While ecological pressures built gradually rather than suddenly, it is possible that both were necessary, a lock and a key arriving in the fossil record at nearly the same time by circumstance rather than single cause. The record itself does not settle the argument, since genes leave no trace in stone, and ecology leaves only indirect signs. This is not a gap to be embarrassed by, but an honest edge of what fossils and DNA can currently tell us. Some mysteries in deep time remain open on purpose. Two of the richest fossil windows into this world lie in Canada and China. Both sites captured something exceedingly rare, moments when soft-bodied animals were buried swiftly enough to leave more than the usual crust of shell and bone. The Canadian site sits high in the Rocky Mountains, while the Chinese site lies in Yunnan province, separated by an ocean and by several million years of Cambrian time. Together, they preserve thousands of species, many represented nowhere else on Earth, from delicate worms to armored predators several times their size. Without these two windows, most of what filled Cambrian seas would remain entirely invisible, since ordinary fossilization destroys soft tissue almost immediately. It is as though two security cameras happened to catch a crowded street that every other record left completely dark. Comparing the two lets scientists see how similar body plans varied across distance and time, filling gaps that either sight alone could not. Rare conditions like these are what let an entire vanished world be seen at all. The Burgess Shale in the Canadian Rockies preserves soft tissue in extraordinary detail. Discovered in the early 20th century, its dark shale layers hold impressions of gills, guts, and delicate limbs that almost never survive the fossilization process elsewhere. The animals here were buried by sudden underwater mudslides, entombed within hours in fine sediment low in oxygen, which slowed decay long enough for their softest parts to leave an imprint. More than 500 species have been identified from this single formation, many so unusual that early researchers struggled to fit them into any known group of animals. Without this accident of geology, creatures like Anomalocaris and Opabinia might be known only as scattered, meaningless fragments, if known at all. A flattened impression in dark rock, barely the width of a hand, can still show the outline of an eye or the curl of a limb. To study this shale closely is to read a chapter of life's history that almost no other place on Earth managed to keep. The mud that buried them became the reason we remember them. The Chengjiang fauna in southern China predates the Burgess Shale by several million years. Its rocks formed in Yunnan province during the earliest stretch of the Cambrian, when animal bodies were still newly arranged into forms we would recognize. Radiometric dating places the site at roughly 518 million years old, some 10 million years older than the mudslides that later buried the Canadian community. This age does not make Chengjiang a rough draft of the Burgess Shale, but a separate and complete record in its own right. Its fossils capture animals closer to the root of the Cambrian radiation, when experimentation among body plans was at its widest. The Burgess Shale shows an explosion already in full swing. Chengjiang shows its opening years. A visitor to that ancient seafloor would have found fewer settled shapes, and more that had not yet found their final form. The explosion, it turns out, had an earlier dawn. Both sites owe their detail to rapid burial in fine, oxygen-poor mud. Across the great distance separating the Rocky Mountains from Yunnan province, the same quiet chemistry was at work beneath Cambrian waters. In each place, storms or underwater slides swept sediment finer than flour over living communities within a matter of hours. This burial did not halt decay completely, it slowed it, holding soft tissue in place long enough for an outline to be pressed into stone. Had the mud carried more oxygen, scavenging microbes would have consumed every soft part before any impression could form. Ordinary seafloor sediment, richer in oxygen, tends to erase nearly everything within days. A creature caught in that fine mud kept its shape the way a leaf keeps its shape when pressed flat between pages. 2 oceans, 1 accident, repeated twice. Such rare deposits, called Lagerstätten, preserve soft bodies almost never fossilized elsewhere. The German term means, roughly, storage place, and geologists use it for any site where preservation reached this unusual level of completeness. Fewer than 20 such deposits are known from the entire Cambrian period, scattered across 4 continents and separated by millions of years apiece. They are not spread evenly through time, and whole stretches of the Cambrian have no Lagerstätte at all, leaving those years nearly silent in the record. A single such deposit can preserve an entire community, gills, guts, and limbs included, rather than the shells that ordinarily survive alone. Most fossil beds hold only hard parts. A Lagerstätte holds a living scene. Finding one is closer to being handed an open window than being handed a locked door. The rest of the Cambrian world rarely receives that chance. Without them, most Cambrian animals would survive only as scattered shell fragments. Ordinary fossilization favors hard material, so a typical seafloor community leaves behind little more than shell, tooth, or the trace of a burrow. At most Cambrian sites, 90% or more of the original community, anything soft-bodied, is thought to be missing entirely from the rock. This is not because those animals were rare in life, but because their bodies simply had nothing durable enough to leave behind. Soft-bodied creatures likely outnumbered shelled ones through much of the Cambrian seas, yet they are the very ones most often erased. A shell can last for hundreds of millions of years. A worm's body usually lasts for hours. Reading only the shells, then imagining the full community, is like reconstructing a forest from nothing but its fallen bark. Most of the Cambrian's soft-bodied majority remains, to this day, unseen. The Sirius Passet site in Greenland preserves an even older Cambrian community. Its rocks lie in the country's remote north, far above the Arctic Circle, exposed only briefly each year when snow retreats from its slopes. Dating places this deposit at close to 518 to 520 million years old, among the very earliest windows into animal life after it diversified. Despite the cold and difficulty of reaching it, its shales preserve soft tissue with a clarity that rivals both Chengjiang and the Burgess Shale. Because it sits so early in the Cambrian, it captures a community closer still to the first branching of major animal groups. Where later deposits show a world already crowded with variety, Sirius Passet shows that variety only beginning to take shape. Reaching the site still requires travel by helicopter, and only a handful of expeditions have ever collected fossils there. Its animals waited under Arctic stone for 500 million years before anyone found them. Comparing these sites lets researchers trace how quickly body plans changed over time, because Chengjiang, Sirius Passet, and the Burgess Shale span several million years of Cambrian history. Together, they form a rough timeline rather than a single snapshot. Certain groups, such as early arthropods, appear in slightly different forms at each site, letting scientists follow small changes in limb number or body segmentation across those years. This comparison does not give a perfect record, since gaps of 1 million years or more still separate one deposit from the next. Even so, it offers something no single site could provide alone: a sense of motion within what once looked like a single frozen moment. Museums often display these fossils side by side, arranged not by size or beauty, but by age, to show that motion directly. Standing before that row of cases, a visitor can watch one body plan quietly shift into another across a handful of shelves. The explosion was not still. It was caught briefly at several different points in its stride. The Cambrian explosion was not one event, but a series of overlapping radiations. The word explosion suggests a single instant, yet the fossil record shows several distinct pulses of diversification, layered one atop another. Researchers often divide the period into stages with names such as Fortunian and Series 2, each marked by its own surge of new body plans. This does not mean the changes were slow in any ordinary sense, only that they were not simultaneous across every lineage at once. Some groups radiated early and then settled, while others took millions of years longer to reach their own burst of variety. A single word, kept for convenience, has flattened what was really a staggered unfolding into something that sounds instantaneous. Looked at closely, the explosion resembles less a single blast than a string of fireworks set off one after another. Even sudden change, in deep time, can still take its time. Diversification continued in waves across roughly 25 million years. This span, though brief by the standards of the planet's history, still stretched far longer than any single human institution or language has ever lasted. The interval runs from around 539 million years ago to about 514 million years ago, based on the layers where new fossils first appear. 25 million years feels vast to imagine, and yet, compared to the more than 3 billion years that life had already spent as simple cells, it was startlingly short. Within that window, nearly every major animal group alive today found its first representative, however small or strange that representative looked. A single human lifetime could be repeated more than 300,000 times within this same stretch of years. Set against the full span of the planet's history, it remains a narrow sliver, brightly lit against a much longer darkness. Most of the shapes life would ever try were sketched out in that short, crowded window. Many strange early body plans quietly vanished before the period's end. Creatures such as Opabinia, with 5 eyes and a single flexible nozzle instead of jaws, left no descendants that can be traced into later oceans. Of the dozens of unusual forms catalogued from sites like the Burgess Shale, a large portion appear to represent entire lineages that ended within the Cambrian itself. Their disappearance was not the result of any single catastrophe, but seems instead to reflect the ordinary sorting of forms that worked less well than their neighbours. Extinction here served the same quiet function it always has, closing off certain paths so that others might continue relatively unobstructed. A design that seems remarkable to us today may simply have been outcompeted by a slightly steadier alternative in its own time. Nothing about their strangeness marked them for failure. Plenty of stranger designs did survive. The Cambrian seas simply tried more doors than the ones that stayed open. Later animals refined rather than replaced most of these early experiments. The major body plans present today, segmented bodies, jointed limbs, internal skeletons among them, were nearly all sketched out in some early Cambrian form before the period closed. What changed afterward was less the basic architecture and more its details, such as limb number, shell shape, or the arrangement of sensory organs along the head. This means the strangest Cambrian animals were not failed drafts of modern ones, but working versions of the same underlying plans, tested under different conditions. Insects, crabs, and even vertebrates carry, somewhere in their ancient ancestry, a body arrangement that first appeared in those crowded early seas. A smartphone's basic shape has changed little in 20 years, even as everything inside it was rebuilt many times over. Evolution, it seems, favors adjustment over invention once a working design has already been found. The blueprint came early. Everything since has been revision. Oxygen levels dipped later in the period, possibly stressing marine ecosystems. Geologists trace this decline through subtle shifts in sulfur and carbon isotopes preserved in shale from several continents, with some records suggesting dissolved oxygen fell by as much as a fifth in affected basins. The exact severity is hard to pin down, since oxygen levels varied by depth and location, even within a single sea. Still, many bottom-dwelling creatures appear to have thinned out during these episodes, retreating from deeper basins towards shallower, better oxygenated water near the coast. Today's oceans hold oxygen levels that fluctuate gently by comparison, buffered by circulation patterns that took hundreds of millions of years more to stabilize. Standing on a Cambrian shoreline during such a dip, the sea might have looked much the same, glassy and full of movement, even as its deeper reaches slowly emptied. The surface gave nothing away. Whatever struggled below did so out of sight, in water no eye would ever see. Several smaller extinction pulses interrupted the Cambrian's overall rise in diversity. These were not single dramatic collapses, but a series of quieter downturns, each trimming back certain lineages before diversity resumed its climb. Geologists have identified at least 4 such pulses spaced across the Middle and Late Cambrian, most visible in the shifting fortunes of trilobites and other shelled creatures. Their causes differ from event to event, and in most cases the record offers only partial answers. What each pulse shared was a pattern of loss followed by recovery, as surviving lineages spread into space left behind by those that faded. This rhythm of contraction and renewal looks nothing like the single sweeping catastrophes that would later end entire eras. It resembles instead a garden thinned repeatedly by frost, never destroyed, only reshaped season after season. Some family of trilobites would vanish quietly from the rock, and within a few million years, another had already taken its place beneath the waves. One such pulse sharply reduced trilobite diversity near the period's end. Trilobites had been among the most successful and abundant animals of the Cambrian seas, their segmented bodies armored, and their eyes among the first compound lenses in the fossil record. Near the boundary of the Thuringian, the Cambrian's final stage, several major trilobite families disappear from the rock within a narrow span of layers, replaced by a smaller set of forms that carried on into the next age. The drop is large enough to stand out clearly in collections gathered from Scandinavia to South China. Whether this was driven by climate, competition, or some combination of both is difficult to say from fossils alone. What survived tended to be smaller and more adaptable, suited to a narrower but steadier way of life. The great trilobite dynasties of the early Cambrian gave way to humbler descendants. Grandeur, it seems, is no guarantee of continuation. Its cause remains uncertain, possibly tied to shifting ocean oxygen and heat. Researchers studying the rock around this trilobite decline have found signs of both a warming pulse and a drop in oxygen reaching into shallow shelf waters, though which came first, or whether one caused the other, is not settled. Isotope records suggest sea temperatures may have risen by several degrees within a geologically short interval, a shift that could have pushed oxygen-poor water up from the depths into habitats once thickly populated. We do not know with confidence whether this warming was the trigger or simply a companion to some other unrecorded change. Fossils can only tell us so much about causes. They are far better witnesses to outcomes. What remains clear is that the seas afterwards supported a different mix of life than they had before. The exact chain of events is lost to us, folded somewhere into rock that no longer speaks clearly. Some questions in deep time stay open forever. The Cambrian gave way to the Ordovician period, roughly 485 million years ago. This boundary is not marked by a single dramatic event, but by a quiet shift recorded in the fossils of tiny eel-like creatures called conodonts, whose changing tooth-like structures give geologists a precise marker in the rock. Life did not pause at this line the way a chapter break might suggest. The seas of the earliest Ordovician looked, at first glance, much like those of the Cambrian before them. Trilobites still crawled the seafloor, and brachiopods still filtered the water for food. Yet, beneath this surface continuity, something had already begun to change, as new groups of animals started testing forms that would soon overtake the old order. A boundary like this exists mostly for those of us looking back, drawing lines where the rock itself simply continues. The Cambrian did not end so much as thin quietly into what came next. Life's diversity climbed even higher during the radiation that followed. Within the first 25 million years of the Ordovician, the number of marine animal families roughly tripled compared to their Cambrian peak, according to counts drawn from thousands of fossil sites worldwide. This surge, sometimes called the Great Biodiversification, produced reef-building corals, more complex mollusks, and swarms of new arthropod and echinoderm forms that spread across shallow seas on every continent. It built directly on the body plans the Cambrian had already established, filling in ecological space that earlier animals had only sketched. Where Cambrian seas held a handful of experimental designs per neighborhood, Ordovician seas held crowded, layered communities, with far more species sharing the same patch of seafloor. The world's oceans, once relatively sparse even at their busiest, became genuinely dense with life for the first time. It was less a new invention than an unfolding of everything the Cambrian had already begun. Nearly every major animal body plan alive today traces back to this period. Zoologists recognize roughly 30 broad groupings of animal life, called phyla, distinguished by fundamentally different body architectures, and the overwhelming majority of these first appear fully formed in Cambrian rock. Segmented worms, joint-legged arthropods, shelled mollusks, and early relatives of starfish and vertebrates all have their earliest confirmed representatives from this single, narrow span of geological time. No comparable burst of new body plans has occurred since, despite more than 500 million years of subsequent evolution. This suggests that most of the fundamental ways an animal body can be organized were discovered once, early, and then kept, rather than reinvented again and again through the ages that followed. Every animal a person has ever seen, in a garden, an aquarium, or their own reflection, belongs to a lineage whose basic shape was already settled in those Cambrian seas. The library of animal forms was written early, and it has rarely needed a new chapter since. The hard parts first evolved here still define most animal fossils since. Shells, spines, and mineralized skeletons appeared rapidly, within perhaps 10 million years near the start of the Cambrian, built largely from calcium carbonate and calcium phosphate drawn from seawater into living tissue for the first time at scale. Before this innovation, soft-bodied animals left only rare and exceptional traces, preserved solely under unusual conditions like those at the Burgess Shale. Once hard parts became common, the fossil record itself changed shape, filling with shells, plates, and exoskeletons that could survive burial, and time far more reliably than flesh ever could. This shift means that almost everything known about animal life from the Cambrian onward comes filtered through whatever happened to carry a hardened part. Soft tissue, then and now, remains the rarest story in the rock, glimpsed only when conditions align just right. The record since that innovation is, in large part, the story of what could be built to last. Modern eyes, limbs, and skeletons all echo designs first tested in Cambrian seas. Compound eyes made of many individual lenses appear first in early arthropods, like trilobites, some possessing over 100 lenses per eye. A design still found today in insects and crustaceans across the world. Jointed limbs, useful for walking, swimming, and manipulating food, likewise emerge in this same window of time, later refined into the legs of spiders, the fins of fish, and eventually the limbs of every land animal descended from them. Internal skeletons, too, have roots reaching back to small Cambrian chordates, whose simple supporting rods anticipated the backbones of every vertebrate since. It is as though evolution assembled a toolkit in those first crowded seas and has been drawing from it ever since, swapping proportions and materials, but rarely inventing an entirely new tool. A person's own eyes and the joints in their fingers carry forward decisions made in water that dried up long before there were fingers to bend. Rock layers in Wales, Canada, and China still hold the record of that first great flourishing. The Slate Hills of Wales gave the period its name, taken from the Cambrian mountains where these layers were first formally described. The Burgess Shale of British Columbia preserved a snapshot of soft-bodied life, so detailed that scientists still study its impressions for hints of ancient anatomy. In southern China, the Chengjiang fossil beds captured an even earlier moment, several million years before the Burgess Shale, in equally fine detail. Together, these three sites, separated now by oceans and continents, once lay far closer together on a warm, shallow sea near the equator. What survives in their stone is a fraction of what once lived, filtered by chance, pressure, and time. Yet it is enough to trace the outline of an entire lost world. The seas that built those bodies are gone, but the rock remembers what the water could not keep. Somewhere in that stone, the first bodies are still waiting, quietly, to be found. And so we drift to the end of our quiet journey through the Cambrian seas. From the first rush of new body plans that scientists call the Cambrian explosion, to the moment eyes first opened and hiding became a necessary skill for the first time, to Opabinia drifting past on its 5 eyes and its long, flexible nozzle, reaching for food no creature before it could have found in the dark. These are the images this world leaves behind, small and strange and endlessly patient. This world teaches something quiet about beginnings. Complexity did not arrive gently or gradually here. It arrived in a burst, as though the ocean had been waiting for permission. And once oxygen rose high enough and the mud softened into something animals could move through, life simply began trying on new shapes. There was no plan to any of it. There was only the slow accumulation of small advantages, tested against the currents of a warm and shallow sea. Imagine standing on the soft, churned floor of that ocean, the mud shifting under a foot you do not have yet. Imagine the hush of that water, broken only by the quiet drift of soft bodies with no bones to announce them. Imagine the first eye opening somewhere nearby, and the stillness that must have followed as every soft-bodied thing nearby learned, for the first time, what it meant to be seen. This is the comfort of science told slowly. The world is stranger, richer, and more interconnected than we can ever fully see. And the Cambrian seas remind us that even our own bodies, our eyes, our symmetry, our sense of up and down, were once new inventions, tested quietly in water none of us will ever touch. If you enjoyed this slow drift through the Cambrian seas, feel free to like and subscribe, or leave a thought in the comments below. It helps others find their way here too, one sleepy soul at a time, drifting off to older and quieter worlds. But for now, there is nothing more you need to do. You can allow the story of the Cambrian seas to fade like the last light of day, leaving only calmness behind. If sleep comes, let it carry you gently. If you are still awake, you are welcome to stay, to listen again, or to let the next video continue your voyage into the quiet wonders of the deep past. Rest well, and remember, somewhere in a slate hillside in Wales, or a shale bank in British Columbia, or a quiet quarry in southern China, the first bodies the world ever built are still resting in the stone, patient, unhurried, waiting for no one in particular. Good night.